stellar mass black hole. This is the most common kind, and the one most people picture when they hear the words. It forms when a giant star, many times heavier than our sun, runs out of fuel and can no longer hold itself up. The core collapses in an instant. The outer layers blow off in a supernova, and what is left behind is a point of gravity so strong that nothing escapes it, not even light. The edge of that trap is called the event horizon, the boundary where there is no coming back. A stellar mass black hole usually weighs somewhere between 5 and 50 times the mass of the Sun, all crushed into a region smaller than a city. One of the first ever found sits about 6,000 light-years away, in a system called Cygnus X1, quietly pulling gas off a nearby star, intermediate mass black hole. This one is the missing piece in the middle, and for a long time, astronomers weren't even sure it existed. It is far heavier than the black holes that come from dying stars, but much lighter than the giants found at the hearts of galaxies, falling somewhere between 100 and 100,000 times the mass of the Sun. They are hard to spot because they tend to hide inside dense clusters of stars, where their pull is easy to confuse with the crowd around them. Recent evidence has pointed to one lurking inside a cluster called Omega Centauri, and gravitational waves have caught two smaller black holes slamming together to make one in this size range. They matter because they may be the seeds that slowly grow into the largest black holes of all, supermassive black hole. These are the heavyweights of the universe, weighing anywhere from 1 million to several billion times the mass of the Sun. Nearly every large galaxy seems to have one sitting at its center, including our own. The one at the heart of the Milky Way is called Sagittarius A star, and it holds about 4 million suns worth of mass in a calm, slowly turning ball of gravity. The first black hole ever photographed was an even bigger one in a galaxy called M87, captured in 2019 as a dark circle ringed by glowing gas. What still puzzles scientists is how these giants got so big so early in the history of the universe. Whatever the answer, their gravity helps shape the entire galaxy that surrounds them. Primordial black hole. This one did not come from a dying star at all. The idea is that in the first fraction of a second after the Big Bang, the young universe was so dense and uneven that some regions simply collapsed on their own, pinching off into black holes before a single star had ever formed. If they exist, they could come in almost any size, from lighter than an asteroid to far heavier than a mountain. No one has confirmed one yet, but they remain one of the leading suspects for dark matter, the invisible material that seems to outweigh everything we can see. Finding even one would tell us something deep about the universe's very first moments. Micro black hole. As the name suggests, this is the smallest kind imaginable, with a mass that could be as tiny as a single mountain, crushed into something smaller than an atom. They are purely theoretical for now. What makes them strange is that the smallest black holes don't last forever. They slowly leak energy and shrink over time, a process predicted by the physicist Stephen Hawking, and the tiniest ones would evaporate away in a flash. There was once a worry that powerful particle colliders might accidentally create them, but even if they could, such a black hole would vanish far too fast to harm anything. They sit at the strange meeting point between gravity and the rules of the very small. Schwarzschild black hole. This is the simplest black hole that math allows, and it was the very first one ever described. Just months after Einstein published his theory of gravity, a German physicist named Karl Schwarzschild worked out what would happen to space if you crushed a mass into a single point. The result was a perfectly round black hole that does not spin and carries no electric charge, defined by its mass alone. At its center sits a singularity, a point where the matter is squeezed down to no size at all, and the known laws of physics break down. Real black holes almost always spin, so this one is more of an ideal starting point than something we expect to find. But it remains the foundation everything else is built on. Kerr black hole. This is the version that better matches reality, because real black holes spin, often incredibly fast. It is named after Roy Kerr, who solved the equations for a rotating black hole in 1963. The spin does something remarkable. It drags space itself around with it, like a spoon stirring honey in an effect called frame dragging. Around a spinning black hole, there is a region where you simply cannot stand still, no matter how hard you try, because space is being pulled along. The singularity inside is stretched from a single point into a ring. The spin also stores enormous energy, and in theory, that energy could be tapped. Almost every black hole we observe is a Kerr black hole of some kind. Reissner-Nordstrom black hole. This one is a theoretical cousin, defined by electric charge instead of spin. It does not rotate, but it carries a net electric charge, and that charge changes its structure, giving it two separate horizons rather than one. In practice, astronomers don't expect to find a strongly charged black hole in the wild, because a charged object floating in space would quickly attract the opposite charge and cancel itself out. Still, it is an important piece of the puzzle. By studying the charged case on paper, physicists learn how these three basic ingredients, mass, spin, and charge, each leave their own mark on the shape of space around a black hole. Kerr-Newman black hole. This is the most complete black hole that the equations allow, combining all three properties at once: mass, spin, and electric charge. It is the most general solution to Einstein's gravity, and every other type is really just a simpler version of it with one or two ingredients switched off. What is striking is how little it takes to fully describe one. No matter what fell in to create it, a black hole can be summed up by just those three numbers, an idea often phrased as the rule that a black hole has no hair. Everything else about whatever it swallowed is erased. That simplicity is one of the strangest and most beautiful facts in all of physics. Binary black hole. This is not a single object, but a pair, two black holes locked in orbit around each other. Over millions of years, they slowly spiral inward, circling faster and faster, until they finally collide and merge into one. That violent merger sends ripples through the fabric of space itself, called gravitational waves, that spread out across the universe. In 2015, detectors on Earth felt one of these ripples for the very first time, from two black holes that had merged more than 1 billion years ago. It confirmed a prediction Einstein made a century earlier, and opened up an entirely new way of studying the cosmos, by listening to it instead of just looking. Rogue black hole. Most black holes we study are either feeding on gas or sitting at a galaxy's center, which makes them easier to find. A rogue black hole is one that wanders alone through space, drifting between the stars with nothing falling into it. They can be flung out of their home regions by powerful gravitational kicks during mergers, or simply born in isolation. Because they give off no light and feed on nothing, they are nearly impossible to see directly. The way astronomers catch one is by watching for the moment its gravity bends the light of a distant star passing behind it, briefly warping that starlight like a lens. There may be many millions of these drifting through our galaxy unseen. Extremal black hole. This is the theoretical edge of what a black hole can be, spun up or charged to the absolute maximum the laws of physics will allow. Push a black hole's spin or charge right up to that limit, and it starts to behave very strangely. Its temperature drops all the way to zero, meaning it would stop leaking energy and effectively never evaporate. Its event horizon thins down to a razor's edge, sitting right on the verge of vanishing entirely. No one expects to find a perfect example in nature, but these extreme cases are deeply useful to theorists. They appear again and again in the search for a deeper theory that could finally unite gravity with the physics of the very small.